Hey class, Mr. Moyden here with a video preparing us for our next unit regarding trigonometry. So let's go ahead and dive in. Just a bit of background in terms of what this subject is all about. What does this new word mean? Just the etymology. Trigon is Greek for triangle. And metron, like geometry, deals with measure. So we're dealing with triangle measure, lengths, angles, sides, all of this stuff. Not just for its own sake, there's some of it is just purely mathematics, but also quite a few applications. Really more, this is just some background for what your general knowledge. But really what is trigonometry? Like all math, it deals with recognizing and using patterns, and also periodic behavior. Something sort of special about trigonometry, this idea of being periodic, meaning every so often things start to come up again. And we'll see that in action in a couple of days. Periodic behavior that appear among the side and angle relationships in right triangles. So recognizing structure and behavior and patterns and then applying them in both real, pure math and also applied math contexts. So let's go ahead and dive into some of the background you'll need to better understand trigonometry. Here you have a seemingly simple question. What's the biggest angle of the shape, the smallest angle, and the medium-sized angle? And without any measurements here, it's a bit of a vague question with a vague answer, perhaps. But if we do what's often good in mathematics, and that's to exaggerate some of the proportions, therefore getting a better picture of what is really the relationship here, then this might show us a better picture. So quite obviously there is a longest side of this figure. This is the longest side. It's the longest line in this shape. And I know it says angle over here, but notice the relationship with the angle it's across from. That's a 90-degree angle. This is acute, and this is acute, and those are certainly smaller than 90. So it appears that the longest side and the biggest angle seem to have this direct opposite or across from type relationship. So that's peculiar, perhaps. Let's look at the other extreme, which is the smallest side length. Well, it makes an angle here, but look at the angle it's directly, once again, across from. It's across from this very narrow, small, sharp angle over here. So that's pretty neat. And then finally the side that's pretty long, but not as long as the longest side, would be this here. And the only angle we haven't connected it with is this angle here, which is not as big as the 90, certainly, right? But it is nevertheless larger than this very tiny, almost closed angle over there. But if you imagine an even more exaggerated case, a very, very, very skinny, long right triangle, right? You have a very large angle here. Of course, you have the largest of these 390 there, and you have a tiny angle, and therefore a tiny short little side there. So keep in mind that these things are, asking about angle sizes. Well, all three of them you can answer sort of the same way. Across from longest, shortest, and mid-sized lengths, side lengths. All right, so you have this nice relationship where the biggest angle and the biggest side are across from each other, and so on and so on. Just as a brief review, this is true for all triangles, not just right triangles. Here you have a right triangle, but notice if I make it no longer right, it's still true. The shortest side here is 11.1, and the smallest angle is 42. The biggest angle is 70. The longest side is 15.7. If I have two angles that are the same, try to get this to work. There we go. Two angles that are the same. Well, what do you know? Two sides that are across from also the same. We've already seen this in the case of the isosceles triangle. And of course, an equilateral triangle has all three angles and all three sides equivalent for similar reasons. If I make another extreme case, this angle here is 162, very big, and look how long the opposite side is. This angle here is very small, a mere 7 degrees, and this length of 10.2 is the shortest of the three. So just some basic background knowledge regarding side and angle relationships. Moving forward into some basics. We're going to be using a new symbol quite a bit, really from here on out, but especially the next several days, and that deals with this thing here called theta. So how do you pronounce this letter? It's called, the symbol is called theta. It's a Greek letter. It comes from the Greek alphabet, and it makes a TH sound in that alphabet. So if you're familiar with Greek from other classes or what have you, you've seen this before. And we use it in mathematics, and we have for several thousand years, in the same way that people typically use the letter X for side lengths or the unknown lengths, right? So how long is something, or what's the missing number? People usually use X for that. Likewise, when we're dealing with not just missing numbers, but a specific angle, right? A number that represents an angle, then we typically use theta in reference to it. All right? So it's a variable that you'll see quite a bit of. In fact, we'll see it right here. A seemingly simple question: what is the side length? And I've labeled them A, B, and C. Directly opposite angle theta. So opposites, when we deal with location and orientation in geometry, opposite here means across from. Well, we've seen that before with like vertical angles and such. So opposite meaning across from. Well, really, what you're across from depends on where you are, right? If you change locations, what you're across from likewise changes. So that's why this is an important distinction. Opposite of what? Opposite from reference to angle theta. So from this position, what's directly across from us? Well, imagine looking out from here, you'll see the letter B. So there's your answer. Now contrast that with this. If I were instead putting theta over here, right, so maybe I'll call this like theta 2 or something, then what's opposite that angle? Well, that would be this side over here. So it all depends on where you are for what is across from you. Again, just common sense, but just a little bit of terminology with that common sense. Another phrase we've seen before, although in a somewhat different context: what is the side length adjacent to angle theta? Well, adjacent, if you recall, means attached or next to. So next to, in a sense, is what this word means. Again, also depends on where you are. If you change locations, things near you or next to you are going to change as well. So from here, what am I next to? Well, that's a little bit you could go two ways. In a sense, letter C, side length C is next to me. B is all the way across, so that's not going to be it. And A is also sort of next to me, right? So you might think, well, maybe it's both, or maybe it's either one, or maybe there's no real answer. Well, let's think. Do any of these side lengths have special names already? Well, hopefully you know that this side length here already has its own special name. We'll get to that in just a moment. You already know what it is, though. But it's this length that doesn't have a special name, so let's kind of bad for it. Let's call it the adjacent side. So the answer to this question would be A. What is the side length adjacent to, attached to, next to this angle? Yeah, C is next to it, but it already has a name, so let's give it to A. And in general, we're talking about the legs when I say side length here. Because if I were referring to the longest side, I'd give it its name, which of course we know is the hypotenuse. So if you think about it, this phrase here, what is the hypotenuse relative to this angle, is not needed. Because no matter where my reference angle is, the hypotenuse is still C, right? So I could be using this frame of reference, in which case opposite is B, adjacent is A. If my angle is here, then opposite is A, next to or adjacent is B. Unchanged in all of this is the hypotenuse, which is the side across from 90, the longest side of a right triangle. So hypotenuse here is C in this particular shape. So with that said, let's try to begin to apply this in a specific context. What can you say about these two triangles? Well, hopefully right away you know they're right triangles, so that's a pretty good observation. Moreover, they also have these angles here. I don't know how big they are, so I'm using a symbol called theta to represent the unknown angle, but I know they're the same because I'm using the same symbol. Right? Just as x is the same as other x's in a specific problem, well, here these two thetas refer to the same angle. Well, you might go a step further and say, okay, well, these shapes look a lot alike. 90s match, some other angle matches. Well, that sounds very much like what we used to call, what we still call angle-angle similarity, isn't it? So these two triangles are indeed similar. So in right triangles, you already have the 90 sort of established already. Those are all, by definition, let's say, right triangle name. And as long as one of the other angles matches, then you already know that they're going to be the same shape. So in a way, dealing just with right triangles, as long as these match, you're dealing with similar figures. Same shape, different sizes. So let's think about how you make similar shapes. So we talked a lot about, this was before winter break, about the idea of dilation and similarity transformation. So imagine you dilate this smaller triangle, which I've now labeled its sides, and make a larger version of it by some scale factor. And I'm calling that scale factor k. Right? So k represents here, just a bit of background, scale factor. And to maintain proportion and make sure I make it a similar figure, not a distorted, warped version of it, I'm going to multiply all of my side lengths by this same number k. So a becomes k times a, b becomes k times b, and c becomes k times c. And if these numbers were different from each other, then they wouldn't be similar, but they are similar, so they're all the same number. Now this may seem like an arbitrary question or consideration, but bear with me for a moment. I'm going to think about, or examine at the very least, what makes this triangle special. What's neat about it? What's unique about it, you could say? Well, what's opposite this angle? So I'm going to consider the opposite side, opposite, and I'm going to compare it to, well, you always want to compare yourself, well actually not always, but in this case I want to compare the line to the longest side, the biggest one. So I'm going to compare it to the hypotenuse. Hypotenuse. So opposite again is relative, and I'm talking about theta, so opposite from theta with the side called A, and the hypotenuse is called C. So in this triangle, this particular ratio is called, is measured as A over C. Okay? Well, this is a bigger triangle, so maybe things will change. Let's find out. From this reference point, what is the side across from me? So once again, still opposite over hypotenuse. Well, opposite is now called Ka, or K times A, and hypotenuse is now called K times C. So I get something that is, looks like it's different. Well, wait a second. I have this K appearing on top and bottom. I'm multiplying by K, I'm multiplying by K, and I'm dividing. Well, hopefully you already recognize these are opposite operations, which is to say, when you divide K by itself, you cancel it out, because K goes into itself once, leaving us with, really, A over C. So the ratio within this triangle, not from one shape to the other, but rather within this particular shape, the opposite to hypotenuse ratio is A over C, the opposite to hypotenuse ratio is A over C. And that's irrespective of what K actually is. I mean, I could have made this a ginormous similar triangle, but it's still opposite hypotenuse, A over C. So in a sense, every wedge shape, right triangle, has this sort of hidden number, and as we'll find, set of numbers within them, right, that sort of describe the shape we're dealing with. Any shape that has this family, right, so they're bigger or smaller versions of each other, has this ratio opposite to hypotenuse. And in this case, it's A over C, although the labeling may differ. So that about wraps it up for our trigonometry preview. One further preview, we'll be seeing this phrase a lot, quite a bit, in the next several days, really from here on out. It's pronounced SOHCAHTOA, and thinking back earlier to the sin, cos, and tan buttons on the calculator and what they really do, you might notice a connection there. Alrighty, hope this helped, and I'll see you in class next week.